doing the subsequent examples on pulleys. Here's a tough looking one, and it is a little tough. It's more just, it's all stuff, we got inclined planes combined with pulleys. And the beauty of this one is it's got friction too. We've got it all in this one. So it's a good one. And we want to find the acceleration of these masses. Okay, so we're given mass 1, we're given mass 2, and we're given the friction between each of these and the surface that whatever this system's on. We know there's no friction at the pulley, but between the masses and the surface. Okay, so we're looking for acceleration. So I decided that positive, it's similar. You can just say there's only one dimension, so to speak. And I'm saying positive, it looks like for sure this is the bigger mass and the steeper incline. It's going to come down this way. Because I'll tell you a headache. A headache would be if I'd made this 30 degrees and this 48 degrees, you'd have to take a guess which one's positive. And in an example with friction, if you end up with a negative acceleration, you have to start all over again. And the reason is that because friction always opposes motion. Hard to explain this without doing it, but if I was mean and I gave you an example or a question on your assignment where this was 30 and this was 48, you did the whole thing, solved it, found that your acceleration was negative, you'd have to stop and restart, do the whole thing over again. Okay? You made a bad guess on direction. This one, it's a given. It's pretty obvious. It's got to be pulled this way, as long as the force down is enough to overcome the friction of the system. Okay, so just thinking about the steps you follow, it's exactly the same. You decide a positive direction, then you do a free body diagram on each mass. That's all I'm going to do. Okay? So this is big, but here's my first mass, the mass 1 here, sorry. And I'm not going to bother with normal and all that stuff. But the thing to remember is there is FK. So normal does matter a bit, but we're going to quickly say, that FK is, remember we know from our inclined planes that normal is mg cos theta, and FK then is normal times mu k, so that's where this comes from. So this really is just Fk equals Fn mu k. Okay, so that's this right here. We also know the net force on this thing is equal to its mass, m1, times acceleration. And just think forward minus backward. Tension's our forward force, and we're subtracting both of the backward forces. Subtract Fk and subtract, remember, this is the downward force. It's not gravity, it's a component of gravity on an inclined plane, mg cos theta, mg sine theta. So it's an eyeful, it's a mouthful, the whole bit, but we're just going to go for it. M1A, so that's our net force, tension, mg, so here's our Fk, here's our mg sine theta. I'm going to get Ft by itself in this equation, that's what I'm looking to do. And so doing that, just rearranging this equation for Ft and substituting 8 for m gives me equation 1. Okay, you might want to pause to write all that down and to maybe process it for a second to make sure you understand it, where all the numbers come from. Please make a star on something if you don't get where it's coming from and ask me in class. But I'm going to move on to the second free body diagram. So on the second one, you've got the force pulling down is mg sine theta, right? On an incline, what pulls you down is mg sine theta. The force pulling up, you've got friction, always opposes motion, and you've got tension in this case holding it back. Okay, so the net force on 2 is m2a, that's just Newton's second law. So I'm just kind of making an equation out of this. Net force on 2 is also forward minus these backward forces, so those are both negative. M2a, that's a mouthful, I won't say it. But what I'm writing here is the forward gravity component minus tension minus friction. Substituting 12 for m2, and I get my equation 2. Okay, so I've got 2 equations now, and I only have 2 unknowns. I'm not putting g is just 9.8, so we know g. And we know mu k is 0.21. So the only unknowns is ft and a. And so what I chose to do, and there's different ways you can substitute, but the way I chose to do it, I'm going to pop up for a second here, is I wrote equation 1 in terms of ft. So this gives me something to substitute into the second equation. So in the second equation, instead of writing Ft, I write this. Okay, so that's what I'm doing here. So I just take this equation, take out the Ft, and put in, this is equation 1. Make sure it's in brackets, you don't make an algebra mistake. Okay. So I'm going to sub in the values for G and the coefficient, 0.21. So pretty much here I just went in this step, then 12a stays the same. This is 12 times 9.8 times sine 48. Okay, that's what this is. There's my minus 8a. This becomes a minus, because a minus is positive. 8 times 9.8 times cos 30 times 0.21 is 14.258. So this here is just this. 8 times 9.8 times sine 30 is right here. And again, these are all just numbers, and it's 16, I'm rounding at points here, but 16.525. So now I'm just going to solve for a. So collect like terms, get a by itself. A is 0.87 meters per second squared. And again, it's not negative, thank goodness, and it's less than 9.8. So it's as reasonable as I can get. It's as much as I can hope for. Okay, so that's acceleration. Actually, that's all we're looking for in this question. We don't have to. If we wanted to find tension, all we'd have to do is take 0.87 and sub it back into equation 1. So imagine that'll take a little bit of reviewing where I got all the numbers from and how it all made sense, but please sort of rewind, take a look at it again, take a look at the equations, and make a star if you want me to help you in class on where I got something. Okay? All right, last example is not a pulley, but I thought it was worth doing. It's specifically solving for tensions, and I like it because it's got I've got 3 masses. So here's an example where this is like, so imagine you've got 3 shopping carts all attached, and they're connected by horizontal cords, okay? And I'm pulling up on an angle, or pretend I'm the store clerk, and I'm pulling up on an angle, and I'm applying 29 newtons. We're assuming there's no friction in these carts. The wheels are brand new, and they work great. So there's no friction, and I want to find the acceleration, this tension, and this tension. So I thought this was a real worthwhile example to do because it's three items that are being pulled, and I got a little bit of an angle in there, so there is a bit of X and Y components in this case. This isn't a pulley, but it is looking at tension. I thought it was a worthwhile example to do. But the strategy is the same as a pulley. You draw the free body diagrams on each, come up with net force equations, assuming the acceleration is constant. But this time, notice, by the way, there's the tensions aren't the same. And the reason is, this cord has to pull all 3 masses. Well, this one only has to pull 2, and this one only has to pull 1. So the tension's not the same in those ropes. There's much more tension here than there would be this very last one. It's only got to pull one 8.7 kilogram cart. Okay, so we have 3 unknowns: the acceleration of the system, this tension, and this one. And so you can guess we're going to end up with an equation with 3 equations, 3 unknowns. So let's do it. So using that strategy, I'm going to do the free body diagram on M1. And we're not going to worry about, there is a Y component because of this being pulled on an angle, but we don't have to do Y direction force balances because it's unnecessary. So looking at the direction of motion on free body diagram 1, I just say the net force on 1 is mass 1 times A. Okay, which is just the second law. That'll be the forward force, which is just, in this case, it's just the X component, the horizontal component of my applied force, or my tension force in that first one, sorry, minus the holding back force, right? So this is all it's acting on is the X component here and FT2. So we're assuming there's an acceleration, so M1 is 9.1 kilograms, times my acceleration is equal to this, and now I have one equation with 2 unknowns. Okay. Going on to the second mass, you can pause if you need to. Going on to the second mass, M2A. This time you look at it horizontally, and I've got Ft2 pulling it this way, and this third tension pulling it back, and that's it. That's only forces. There's no friction, thank goodness. And I'm not worrying about the up and down. I'm just doing force balances in the direction of motion. So M2A is T2 minus T3, forward minus backwards. So now I have a second equation. 12 times acceleration is T2 minus T3. So problem is, with these two equations that I've got so far, I've got 3 unknowns, because A, I've got them both. I've got T2, but I don't have it 3. So you can't solve 2 equations, 3 unknowns. We need another equation. So looking at the third mass, the free body diagram, since there's no friction, there's nothing holding this thing back, all I've got is the tension pulling it forward. Okay? So I've got M3 times A. This is my net force, so that'll be equal to FT3. So just subbing in 8.7 kilograms. Here's my third equation. Okay? So now it's just a matter of algebra. Now you're in grade 10 math. You've got 3 equations, 3 unknowns. We're going to use substitution and solve for acceleration T2 and T3. Okay? So first step, substitute equation 3 into equation 2. So instead of writing FT3 into equation, here's equation 2, I'm going to take out the FT3 and put 8.7a in there. Okay? And then I can sort of rearrange it to get the a's all on this side. That's why it's 20.7a. And I now have another equation with just a and FT2. So I can substitute this equation into equation 1. So here's equation 1. And I have, instead of writing FT2, right? I'm not going to write FT2 in anymore. I'm going to write 20.7a. And then I can rearrange and solve, get a by itself, and a is 0.9. Then, once I know a, I can use this equation, back to this one, to solve for FT2. So now I know the second tension. And back to the third equation, I could then solve, knowing a as well, I can solve for FT3. So then I have my 3 tensions. So again, this last part is just 3 equations, 3 unknowns. I don't really know what a good number for tension, but I think these ones are great, so I'm going to check mark them. Well, 0.9 is a reasonable number. I've always said between minus 10 and 10 is a good number. Tensions, it's hard to say, but why not? They look like good numbers. They're in the realm. They're not a million, so I'll check mark them. Anyways, that's a couple of pulley examples, and hope that helps you with your problem set.